Hey guys, welcome back to chapter 13. We're going to continue our discussion on colligative properties. And today we're actually going to knock out two, but they're very closely related. So we're going to talk about freezing point, depression, boiling point, elevation. But before we dive into those, let's relate this back to vapor pressure, the one colligative property that we already talked about. So vapor pressure lowering occurs at all temperatures. So no matter if it was a cold substance, if it was a warm substance, if we were to measure vapor pressure, it would occur at all temperatures. This idea, though, of vapor pressure lowering has a direct effect on the boiling point. So if you remember, boiling point is when vapor pressure equals external pressure. So vapor pressure equals external pressure. That's why molecules that are at the middle of our solution have the ability to bubble out or turn into vapor and then rise to the top and get released. So vapor pressure is the same as external pressure. Well, with vapor pressure being lower due to colligative properties, so now we're talking about vapor pressure of a pure solvent versus vapor pressure of a solution. So the vapor pressure of that solution is lower. So we're going to have to put in extra energy. We're going to have to put in more work to get that vapor pressure back up to external pressure, back up to being equal to external pressure. So we have to put in a little bit more work to reach the boiling point. That's kind of the moral of this story. So the result is that the temperature required to boil a solution is going to be higher than the temperature of the boiling point of the pure solvent. Hence, boiling point elevation. So, for example, if we have a pure, we have a beaker with just pure water in it. All that's in that beaker is H2O. It will boil at 100 degrees Celsius. But if we were to add anything to that beaker, remember we're talking about number of particles, not necessarily what particles we're putting in. So if we add any particle to make that a solution, the boiling point of water is going to go up. So it could be 101 degrees Celsius. It could be 105 degrees Celsius. But right now, the big take home here is that the boiling point is going to go up. We'll have to get it to a higher temperature before it boils. Okay. So let's talk about freezing. So those are the two that we're going to talk about, boiling and freezing. Let's talk about freezing. So think about water. If we think about having liquid water, we cool that down, we put it in the freezer, we cool that down. What's going to happen is there's going to be intermolecular forces that form that cause that solid to be held into the crystalline structure. So we're going to have these intermolecular forces that form. It's going to lock those water molecules into place to form our crystal, to form our solid. Well, what if we've got particles in there? What if we've made a solution with some sort of particle in there? How is that going to affect the freezing process? Well, in order to form the solid, we need those intermolecular forces to line up perfectly to form our crystal structure. With the impurities in there, with the extra particles in there, we're going to have to move those extra particles out of the way so that we can get our intermolecular forces to line up the proper way. So in order for that particular substance to freeze, we're going to have to do some extra work, right? We're going to have to take those solute particles, move them aside, and then freeze our substance. So we're going to have to make the temperature even lower so that we can move those particles out of the way. Essentially, if you were to freeze an ice cube, for example, so let's say you have a mixture of salt water, and you were to put that salt water into the freezer and freeze it, you would find that the crystal structure in the very middle of that ice cube would be pure water. There would be no salt in there. all of the salt would have been pushed out. So likely the top of that ice cube would be really salty if you were to lick it, as opposed to if you were to break the ice cube and then lick the middle, it wouldn't taste so salty. So that's what we're doing, is we're kind of purifying the solvent and then freezing the solvent. So putting a solute into solution also results in the temperature required to freeze a solution to be lower than the freezing point of a pure solvent. So we've got boiling point elevation, higher temperature, and freezing point depression, a lower temperature. So we'll see this in lab. We're going to do a really fun lab where we're going to actually see in real time the freezing point of something go down. For those of you that are visual, this is a great representation of everything that I've just talked about. So let me get my little pointer here and walk you through this. So the blue line represents what would happen in a pure solvent. So this would be going from solid to liquid or liquid to solid. This would be that freezing point. And here going liquid to gas, gas to liquid, that would be that boiling point, this blue line over here. And what we see is when we add a solute, we move out to the red line, right? So if we add a solute to that solution, now we see that the freezing point or melting point, whichever you want to think about it, the freezing point was right here. Now the new freezing point at 1 atm, now the new freezing point is at a lower temperature. So that's freezing point depression. We've got to get to a lower temperature before that solution freezes. And then same thing over here on the boiling point side. So the blue represents the pure solvent. So this would be the temperature at which it boils. So let's say it's 100 degrees Celsius. Let's say it's water. We add a solute to that mixture. And now the boiling point is out here. And so now the boiling point would be at 103 degrees Celsius. So it would be a higher temperature for that to boil. Boiling point elevation. So now we can answer a couple of our questions that I posed at the very beginning of the chapter. So the first question that I posed is, why do we put salt down when we're expecting it to freeze? So by putting salt down, that's going to create a solution, right? So when that ice hits the ground or water hits the ground, it's going to mix with that salt and create a solution. And we know that the freezing point depression, freezing point is depressed. So if the temperature is dipped down to, let's say, 32 degrees Fahrenheit or 0 degrees Celsius, pure water would freeze. But if we mix the salt in there and we reach 0 degrees Celsius, it's not going to freeze, right? We'd have to get down to like -2, -3 degrees Celsius before it starts freezing. So salt is a good option unless you live in Antarctica and temperatures get well below the freezing point. At that point, salt may not be terribly helpful. But for us here in North Carolina and for most places in the United States, that salt will be helpful in lowering the freezing point so you don't have ice on the roads or you don't have ice right outside your door. So that was the first question. The other question that I posed was antifreeze. So antifreeze actually is a dual purpose in your engine. So we put antifreeze in our car. And antifreeze, again, creates a water solution. So instead of having pure water in the engine block, we've got a water solution in our engine block. So antifreeze is going to prevent the water from freezing. So if your car is sitting outside in a cold temperature on a cold winter day, it's going to allow that freezing point to be depressed. So the water is not going to freeze in your engine block. And then same thing, if your car is sitting outside on a hot day, it's also going to prevent the water from boiling. So antifreeze actually is a dual purpose. It creates a solution and it causes the water to not freeze or boil if we're in a relatively stable situation. Okay. So that's the qualitative look at freezing point depression, boiling point elevation. So that's the qualitative look. We're chemists, so we're going to want to quantify this. We're going to want to deal with numbers too. So here is part of the formula to calculate this. So I'm just going to introduce the formula. I will tell you there is one more variable. We'll get to that in just a moment. But boiling point elevation. So we're going to be able to calculate the change in temperature of the boiling point. So this triangle right here denotes change. T stands for temperature, and that's going to be the temperature of the boiling point. That's what that little b means. So what we are going to calculate is how much the boiling point is going to elevate. So the answer may be 3 degrees Celsius. So what we would do with that number is then take the boiling point plus 3 degrees Celsius would tell us our new boiling point temperature. So we're calculating how much it's getting elevated. Okay. There's 3 variables that are going to be involved in this process. We'll get to the third variable in just a moment. The first variable is the boiling point elevation constant of our solvent. So this is going to be a constant. This is going to be a number that's either given or something that you can look up. Boiling point constants have been very well studied, and so we've got a whole list of we got a whole table, a whole list for the common solvents that we're going to use. So, for example, water is one that's very well known, and so we'll be able to use that one over and over again. The second variable is molality. Okay, so this is why we talked about molality in our calculations of concentration, because that's the variable that we use for this boiling point elevation, freezing point depression. So we're going to calculate the molality. Well, why would molality be a factor in boiling point elevation? So certainly solvent would be a factor. It depends on what solvent we're using. But why would molality matter? Well, we're measuring the number of particles, right? It doesn't matter what particle is dissolved in solution. What matters is the number of particles. So if we have more particles in solution, that change is going to be a bigger change. If we have less particles in solution, that change is going to be a smaller change. So this is something else that we're going to be able to see in real time when we do the lab for boiling point or for freezing point depression, excuse me. Okay. Real quick, just back to this, this constant, again, it changes from solvent to solvent, and really what it measures is the vulnerability to change. So some substances are vulnerable to change. So we add some solutes in and wow, we see a huge change. Some are less vulnerable, so they're a little bit more robust, and so they would have a smaller vulnerability. So that's all that is a measure of. But again, something that's given or something you can look up. What you're going to notice about freezing point depression is that this formula is going to look very, very similar or identical to the boiling point formula. So again, it's going to be 3 variables. We'll get to the third variable in just a moment. But here we're looking at the change in temperature of the freezing point. So change in temperature of the freezing point. One little nuance here is that this number is going to be a negative number, right? So freezing point depression, let's say, again, we calculate this out and we get 3 degrees Celsius. When we're talking about freezing point depression, we know that the temperature of the freezing point is going to go down 3 degrees Celsius, depression, right? So what we would do is we take the freezing point minus 3 degrees Celsius, and that would give us our new freezing point, okay? Again, we're going to have the freezing point depression constant of the solvent. So again, something that's going to be given or able to look up. It is a different number than the boiling point. So that's one thing that you're just going to have to keep an eye on is, am I looking at freezing or boiling? And then go find that constant. So make sure you get the correct phase change. And then again, we're looking at the molality. So again, number of particles, not necessarily what the particle is. Okay. Just to give you an introduction and to give you a place to kind of refer back to, here are some freezing points and then the constants for different substances. So let's start with water, and this is out of your textbook. So if you need to refer back to this, you can look in your text or take a screenshot of this slide. So let's look at water because we're probably the most familiar with water. So water freezes at 0 degrees Celsius. And then if I wanted to know what is the freezing point depression constant for water, it's 1.86. And the units for that should not be shocking at all, but the units for that are degrees Celsius over molality. So what we'll see is these units are kind of funky, kind of different, but when we go to solve problems, it's going to be a very useful unit for us. So 1.86 degrees Celsius over molal. For water, we see the normal boiling point is 100 degrees Celsius. And then the boiling point elevation constant is 0.512. And again, the units are the same, degrees Celsius over molality. Okay. All right, so let's just do a quick example to show you how this is going to work. And then we will add in our last variable. Flip around so I can write on this. All right. So here's our problem. What is the boiling point of seawater if the concentration of ions in seawater is 1.15 molal? Okay. So our formula thus far, and again, we're going to add another variable in just a moment, but we'll rock it with what we know right now. So the change in temperature of boiling, so it's asking about boiling point, is boiling point elevation constant times the molality. Okay. This problem is a straightforward plug and chug as it gave us the molality. Eventually, you'll have to solve for that. So plug in what we know, crank out the number. So boiling point constant is given. It is 0.512 degrees Celsius over molality times the molality, which is 1.15 molal. And what we see here is we got molality on the top, molality on the bottom. So the units of molality cancel. We're left with degrees Celsius, which is helpful because we're solving for a temperature change, right? So that's how that unit helps us out. So let's go ahead and plug this into our calculator. So we've got 0.512 times 1.15 equals 0.59 degrees Celsius. Okay, so that is the temperature change. But let's read this problem carefully. It is not asking us what is the change in temperature, what is the change in the boiling point. What it's asking us for is the boiling point, okay? So we have to go one step further. Water boils at 100 degrees Celsius. But when we add in these ions, that boiling point is going to go up So we're going to add this change to it. So 100 degrees Celsius plus 0.59 degrees Celsius. So the new boiling point is 100.59 degrees Celsius. So if you were to type in 0.59, it would mark it as incorrect because it's not asking for the change. The correct answer is 100.59 degrees Celsius. So it elevated that boiling point just slightly. Okay. All right, so let's get to that last variable in our equation. So the last variable in our equation is also going to address this idea of the number of molecules in solution, okay? So what we have to consider is an electrolyte versus a non-electrolyte. Those are some scientific mumbo-jumbo words. So let's break it down, okay? So a non-electrolyte is going to be a molecular compound. Okay, so that's going to be a non-metal bound to another non-metal. So they're covalently bound. So molecular compound or a covalent bond. Okay. So a non-electrolyte, non-metal bound to another non-metal. We know that the bonding is covalent. It's called a molecular compound. But the big take home here is that they do not dissociate. Okay, so if I put one molecule of sugar into water, it's going to just dissolve in solution as one big molecule of sugar. It's not going to break apart. It's not going to dissociate. It stays together as one big molecule. Okay, so that's a non-electrolyte. And where do we get this electrolyte idea? Well, it does not conduct electricity because there's no charges in there. Okay, so non-electrolyte. Electrolyte, on the other hand, are ionic compounds. Okay, so this is a metal bound to another non-metal. Okay, so with ionic compounds, with metals bound to non-metals, remember that when they come together, there's a transfer of electrons, positives attracted to negative, and that's what holds these compounds together. So the big take home here is when I dissolve an ionic compound or when I dissolve an electrolyte in solution, they are going to dissociate or break apart. So for example, if I put one molecule of salt into water, so that's this, salt is NaCl, it's going to break apart into two ions or two molecules. So we're going to have one salt ion and one chlorine ion. So I put one molecule of salt in, and it's going to break apart, and it's going to allow two molecules to be present. Okay. So if we're concerned about the number of particles in solution, well, this could dramatically change things. So one molecule of sugar is not necessarily the same as one molecule of salt, right? It's going to have different effects on our solution. So the last factor that addresses this or acknowledges this is something called the Vant Hof Factor. So this is going to be the third variable in our formula. So it's going to look like this. Okay, the Vant Hof Factor. So the Vant Hof Factor is the ratio of moles of solute particles to moles of formula units dissolved or moles of molecules dissolved. Okay, so for our sugar example, for every one molecule or formula unit, we put in, there's going to be 1 particle in solution. Okay, so 1 over 1, the Vant Hof factor for sugar would just be 1. Okay, multiplying by 1, not going to change anything. Vant Hof factor for salt, on the other hand, for every 1 molecule or formula unit, we put in, how many particles did that break apart into? Yeah, it broke apart into 2 particles. Okay. So 2 over 1, the Vant Hof factor for sodium chloride is going to be 2. So multiplying by a variable of 2 is going to change things. It's going to make it a bigger change, right? More particles, bigger change. So that's the last variable in our equation. That's the last thing that we need to consider. Okay. So here are some examples of Vant Hof factors. We're going to stick with the expected unless I ask you to solve for Vant Hof. That could be something that I do. But just use the expected values here. So for anything that's a non-electrolyte, it's always going to be a Vant Hof factor of 1. For something like NaCl, that's going to break apart into sodium ions and chlorine ions. Okay. This guy right here. So we need to recognize this. SO4 is a polyatomic ion. So I will, in the helpful handouts, I'll put together a list of polyatomic ions. So for those of you that maybe haven't had chemistry in a while, you can remember what they are. But polyatomic ions are packets of atoms that carry a charge. So this SO2 is a whole packet, and it carries with it a -2 charge. Okay. So when SO4. Yeah, SO4. So when magnesium sulfate, which is this guy right here, breaks apart into solution, it breaks apart into 1 particle of magnesium and 1 particle of SO4. This cannot break down anymore. So that's why the Vant Hof factor is 2, because you got 1 particle, 2 particles. Okay. Something else to consider is our subscripts. So looking at magnesium chloride, remember we need 2 chlorine atoms to balance out this +2 on the magnesium. So if MgCl2 is in solution, it's going to break apart into 1 particle of magnesium and 2 particles of chlorine. So we've got 1, 2, 3 particles in solution. That's why the Vant Hof factor is 3. Okay. So just something that you're going to have to consider, ionic versus covalent. And then if it's ionic, you have to be very thoughtful about the number of particles that get dissolved in solution. Okay. So solutions of electrolytes. For solutions of electrolytes, we need the correct number of particles formed. So the number of ions in the molecule or in the formula unit. And then we see here's our completed formula. So Vant Hof factor is a part of this formula. So when you go to calculate change in boiling point, change in freezing point, this is the formula that we'll use, the one with the Vant Hof factor in there. Okay. So let's end this slideshow with an example. So not a lot of room for me to work on this slide, but I'll let you guys take it in, and then I'll work it on the next slide. So go ahead and pause the video, get as far into this problem as you can, and then I'll catch up to you in just a moment. So I'm going to take inventory of what I need and know, and then start calculating for there. So I'm doing the change in temperature for boiling. My formula is boiling point elevation constant molality, and Vant Hof. Okay, so we're calculating the change in temperature of the boiling. I don't know that. So the constant, we're dealing with water. So I want to come down here to my table. Here's water. Woo, that's not what I wanted to do. Here's water. So this is the freezing point constant. Keep going across. There's my boiling point constant. So I know that it's 0.512 degrees Celsius over molality. Okay. Then we need to decipher molality. Okay. Does it give us the molality? Well, of course not. But it gives us the information we need for molality. So it gives us the number of grams of sodium chloride and the number of grams of water. So let me do a little side calculation over here. So remember, molality equals moles of solute over kilograms of solvent. Okay. So moles of solute, we're going to have to do a grams to mole calculation. So I've got 10 grams of sodium chloride. Grams go down here because that's the unit we're trying to get rid of. Moles goes up here because that's the unit we're interested in. So in 1 mole, how many grams of sodium chloride do we have? So go to the periodic table. Sodium, I don't have a periodic table in front of me. Let me look it up real quick. All right. So molar mass, Na. So the molar mass for sodium is 22.9. The molar mass for chlorine is 35.5. So we add those two numbers together, 22.9 plus 35.5. And the molar mass for sodium chloride is 58.4. Multiply across the top, divide by the bottom. So 10 times 1 divided by 58.4 equals 0.17. Okay, so that's the molality, that's the number of moles. So that's the number on top. So 0.17 moles. Okay. Number on the bottom is kilograms of solvent. So it gives it to us in grams. We just need to convert to kilograms. So let me just use this space again here. So we've got 54 grams. We can do a unit conversion, grams on the bottom, kilograms on top. So in 1 kilogram, we've got 1,000 grams. So 54 divided by 1,000 equals 0.054 kilograms. Or we're moving that decimal 3 places. So 0.054 kilograms. Okay. Plug that into our calculator. 0.17 divided by 0.054. And we get the molality of this solution is 1.5 molal. 3.15 molal, excuse me. Okay. All right, so the last variable is that Vant Hof factor. So sodium chloride, I know, is an ionic compound. Sodium is a metal, chlorine is a nonmetal. So when I put that into solution, it's going to break apart into 2 particles. So I'm going to use the expected Vant Hof factor. So Vant Hof factor is going to be 2. Okay. Now let's plug and chug. So we've got the change in temperature of the boiling point is going to be 0.512. Get rid of this eyebrow. All right. 0.512 degrees Celsius molal times the molality, which is 3.15, and the Vant Hof factor, which is 2. Vant Hof factor, again, is unitless, so that's not going to affect the units in our problem. Here, again, we see molality cancels out, so we're left with degrees Celsius. So the change in temperature of the boiling point is 0.512 times 3.15 times 2 equals 3.23 degrees Celsius. Is it asking us for the change in the boiling point? No, it is asking us for the new boiling point. So the old boiling point of pure water is 100 degrees Celsius. So the new temperature at which this is boiling is going to be 100 degrees Celsius plus the change, 3.23 degrees Celsius. So the correct answer is 103.23 degrees Celsius. Again, if I teach you nothing else, you need to ask yourself, does this make sense? So boiling point elevation, we would expect the boiling point to go up, and it does in fact go up. So that's it for freezing point depression, boiling point elevation. Dive into these problems, practice to make sure that you are proficient at them, because you certainly will see them again. I hope you guys found this helpful.